You're worthless, although I still love you. I'm the best thing that happened to you. You give me blues on purpose. It wouldn't have to be like this.
Hi guys, my name is Nako Nakatsuka. I'm a fourth year chemistry PhD student at UCLA, and today I'll be helping you guys out by going over some general chemistry concepts. And good luck with the course. So distances between centers of bonded atoms are called bond lengths or bond distances. Bond lengths vary depending on many factors, but in general, they're pretty consistent. And so there's often tables of interatomic distances or bond lengths in a lot of standard handbooks, textbooks, and online. So you can find that yourself. And so bond energy is a measure of the strength of a chemical bond. And the larger the bond energy, the stronger the bond. And so to explain it a little more clearly, the bond energy is essentially the average enthalpy change for a gas reaction to break all the similar bonds. And so let's walk you through this now. So weak bonds are longer and easily broken and more likely involved in reactions. Strong or shorter bonds are harder to break and less reactive. We mentioned this before in different chapters, but now we're going to look at it in more detail. So the strength of a bond is measured by its dissociation energy. And this is the energy required to break a bond. And dissociation energies are always positive in values. And so let's look at these three examples. We have C2H6 with one single bond, C2H4 with one double bond, and C2H2 with a triple bond. As you can see, we have the longest bond being 153 picomolar, and we have the shortest bond with a triple bond. On the other hand, for the single bond, this is the weakest bond. And for the triple bond, it's the strongest bond. So we go from the longest and the weakest to the shortest and the strongest. And this is a very important relationship. So let's go over it in a little more detail. So F2 is drawn like so. Fluorine is bound to another fluorine with a single bond. The dissociation energy in this case is 146 kilojoules per mole. And the distance between the two fluorine atoms is 1.42 angstroms. And so in this case, we have one bond, and we have 6 lone pairs of electrons on each fluorine atom. I'll explain in a second why I'm writing this part down as well. So now let's look at O2. You guys know how to draw Lewis structures now, so you know that O2 has a double bond, and then 2 lone pairs on each oxygen. The dissociation energy is 484 kilojoules per mole, and the distance between the two oxygens is 1.21 angstroms. So now we have 2 bonds, and we have 4 lone pairs. As you can see, going from a single to a double bond, we have a dissociation energy that is significantly increased, and we also have a distance that has decreased, which is following the trend that we just talked about over here with the hydrocarbons. Then let's look at N2, which is nitrogen bound by 3 bonds to another nitrogen with 1 lone pair on each nitrogen. The dissociation energy in this case, as you can guess, is going to be higher than these two values, 932 kilojoules per mole, and with a bond distance that we expect is going to be shorter, and it is. And in this case, we have 3 bonds and 2 lone pairs. So the reason why I've been writing out the number of bonds and the number of lone pairs is that in addition to this trend that we can see, I also wanted to mention lone pairs. So lone pairs on neighboring atoms repel each other because you have electrons that are negatively charged, they repel the electrons that are right next to them. And so a higher number of neighboring lone pairs also weakens the bond. And so as you can see, this is increasing in strength of the bond, going from single to double to triple, right? But you can also see the relationship between the lone pairs. You have 6 lone pairs for the single bond, meaning there's a lot of electron-electron repulsion between the neighboring atoms. And then we have 2 lone pairs for the triple bond, meaning that that interaction is a lot less. Another factor I wanted to talk about was that, let's draw a little box right here so as to not confuse you. Okay, so larger bonding atoms means that there's a larger distance between them. And thus, they're going to have weaker bonds. So an example of this would be to look at HF. This has a dissociation energy value of 543 kilojoules per mole. And then let's move on to a larger radius, HCl, which has a dissociation energy, I could say it correctly this time, of 419 kilojoules per mole. And now let's look at HI, which has an even larger radius, and we have a dissociation energy of 287 kilojoules per mole. So the trend I wanted to show you guys here is that when going from a small radius to a larger radius, and again, if you go back to the trends in the atomic size, you'll be able to see that going from fluorine down to chlorine and then iodine, the radius keeps increasing. And the larger the radius, the dissociation energies are decreasing because you have weaker interactions. Larger bonding atoms, larger distances between them, weaker bonds, and thus a lower energy value that is required in order to break the bond between the 2 atoms. And so these are the trends that you need to take into consideration when looking at bond lengths and energy.